Okay, picking up with our summer review packet once again, we're going to move on to even and odd functions. This is on page 5. Maybe one of the most famous even functions of all is f of x equals x squared. And we're going to talk about that in just a moment. But for an even function, what you need to know very simply is this, that f of opposite x is equal to f of x. When we substitute in opposite x into the function, we get f of x itself. This would really be true of y equals x squared. You can see what would happen if we were to substitute in opposite of x in to that function. The opposite of x, when you'd square that, would be x squared itself. So that would be equivalent to f of x. So this would be an even function. If we were to look at that graphically, looking at what a parabola y equals x squared would look like, we'd see symmetry about that y-axis. This function could be reflected onto itself. For an odd function, for an odd function, very similar setup, we're going to say that f of opposite x, what would that yield? Well, not f of x itself, but the opposite of f of x. That's really the definition of an odd function. What you're going to see is, maybe not surprisingly, that the most famous odd function would be y equals x to the third, an odd power. Look what happens as we substitute in opposite x here. Instead of writing an x, we put opposite x in its place. And negative x cubed, well, negative 1 to the third is a negative. This would become the opposite of f of x. So that's what we have for an odd function. What you're going to see very quickly is, for a couple of problems, if we wanted to take a look at that, and you can also take a look at what's happening graphically here. You don't have symmetry about the y-axis or about the x-axis. You'd actually have symmetry about the origin. You could see that to be true. But let's state for these next couple problems whether the function is even, odd, or neither. It's quite possible that you'd get neither. And just want to do two quick problems showcasing that. So for example 1, let's say that I gave you f of x is equal to x cubed plus 1 over x. Well, let's see what happens when we substitute in f of opposite x. By the way, many teachers actually will make this statement about a blank. When you're substituting into a function, wherever you see an x, just leave parentheses there. F of a blank would equal a blank cubed plus 1 over a blank, meaning f of the opposite of x. Well, let's see what we get. Here's opposite of x cubed plus 1 over the opposite of x. Well, opposite of x cubed, well, we could say that's just going to be the opposite of x cubed. Opposite of x down here, you have a negative, but dividing by a negative, we very well could just factor that out. And we would see this to be the case. Now, f of opposite x very clearly is not equal to f of x itself. I think that's fairly obvious. For an even function, again, what you want to see is f of opposite x would equal f of x. We're not getting that. For an odd function, though, we'd have f of opposite x would equal the opposite of f of x. Well, take a look at what we've just written here. I see a negative and I see a negative. I could factor that negative out. I could divide that negative out. And, when I do that, you could see that this would actually yield the opposite of what we have for f of x. So f of opposite x is equal to the opposite of f of x. Therefore, f, that's the three dots there, therefore f is an odd function. By way of comparison, let's take a look at example 2. And what if I'd given you f of x equals 2x squared minus 2x plus 2? Well, once again, we can say what is f of the opposite of x. And we can, wherever we see an x, replace it with the opposite of x. Let's see here. Just clean that up just a bit and see what we get as a result. Now, in the very beginning, you're going to see that the opposite of x squared, when you square that negative, you're just going to be left with x squared itself. A negative squared becomes a positive. Negative 2 times negative x would become plus 2x. Now, I think it's very, very important for us to take a look right now and notice that what we've just achieved, f of opposite x, this is not the same thing as f of x. And in fact, if I were to take the opposite of f of x, I'd change every sign here. I'd be left with negative 2x squared plus 2x minus 2. So in other words, neither of these cases will hold true. F of x is neither even nor odd. So that's just the way many of these functions work. Continuing on, though, I'd like for us to now take a look on the very bottom of that page and take a look at inverses. And just want to do a few problems with inverses with you. Let's go ahead and find the inverse of some of these problems right here. So let's just say that we had f of x equaled the quantity x plus 1 to the fifth plus 8. So this is at the bottom of page 5. You might remember what we do to find an inverse. We replace f of x with y, and then we always switch x and y. Where we have a y, we write it as an x. Where we have an x, we write it as a y. So when we're finding the inverse of a function, we're always going to do that. What do we do next? Well, we solve for this new y. We get this new y alone. To do that, I'm going to subtract an 8 from both sides. And we're very close to getting this y all by itself. It's just that it's trapped inside this fifth power. You might wonder how we can undo a fifth power. The answer very quickly is to take a fifth root on both sides. So to get rid of a fifth power, we'll take a fifth root. The left-hand side becomes the fifth root of x minus 8. The right-hand side just becomes y plus 1. Then what? Well, we'll minus a 1 from both sides. And very quickly, we have the fifth root of x minus 8. Then we have minus 1. What you would see written out, though, is that replacing y with the symbol f negative 1 of x, read the f inverse of x, is really what would be expected for us to do as a final step. Okay, let's take a look at another problem, very similar. For example 2, let's say we wanted to find the inverse of f of x equals the cube root of x plus 1 all over 5. And once again, what we start by doing is writing f of x as a y. You might remember what we did starting this off then. We switch x and y. Where we have a y, we write that as an x. Where we had an x, we replace that with a y. And then we need to solve for our new y. But here we go again. It's working in a different direction. Now we need to eliminate a cube root. You might wonder how to get rid of a third root. The answer will be to raise to a third power. And great algebra review right here. Cubing a cube root will make it go away. And then we'll just have y plus 1 all over 5. Tell you what, that's x cubed all over 1. You can cross multiply if you would like, or just multiply both sides by 5. That would work. Now minus a 1, and you'll have y is equal to 5x cubed minus 1. But you might not be surprised, we're going to finish this off by writing f inverse, f negative 1 of x, of 5x to the third minus 1. Okay, we do have a little bit of time. Maybe we could do one final inverse problem, and I think that would be a good way to wrap up. Let's get a little more space here. Last example, find the inverse of f of x equals 5 all over x minus 1. And we'll just say find the inverse. Well, here we go again. Write f of x is y. Switch x and y. And at this point, maybe this would be somewhat helpful. I hope it would. We talked about cross multiplying before. Let's do that now. 1 times 5 would equal x times y minus 1. And just to help you out, I think sometimes kids want to distribute the x. You certainly may. You certainly may. But remember, ultimately, I want to get y alone. So this might surprise you a little bit. Even though you could distribute the x, I'm going to divide both sides by x right here. That might make this problem look a little bit nicer. Look at that. Then what? Very simply, add a 1, and you'd have 5 over x plus 1. Final answer, f inverse of x equals 5 all over x plus 1. Sometimes kids will wonder if they'd get exactly the same answer if they would have distributed the x. Let's take a look and see. If you would have done this work instead, sometimes kids really want to do that. They'll say, I would have multiplied by x, and I'd say, that's fine, you can do that. Then kids would say, well, then I'd want to add an x. You know, I'm trying to get y all by itself. I'd say, sure, you could do that. And then, as a final step, kids would say, well, to get y by itself, I'm going to divide by x. And you certainly may do that. Now, at first glance, this can be a little scary because kids will look at this and they'll say, well, that's not what you have. You've got a different answer. But if you really think about it, 5 over x plus 1, if you got a common denominator, put it all together, you'd get exactly the same thing. So just wanted to show you page 5 on this review packet. Hope it's going well for you. We'll be picking up with some graphing material very, very soon.